Hi everyone, this is the third example of chapter 5.4, and again it's involved two optical devices. In this case, a converging and a diverging lens. So let's read the question and then we're going to solve that one. Question 97. A converging lens L1, so we denote both lenses, so this one is L1, the diverging lens is L2. With a converging lens L1 with a focal length of 0.4 meter and a diverging lens L2 with a focal length of minus 0.25 meter are separated by 0.6 meter. A light bulb is located 0.8 meter in front of the first lens. Find the magnification and the distance from the second lens of the image, actually of the final image in this case. So here we have all the relevant information that we are given. The distance here, D1, is the distance of the object, basically 0.8 meter. The distance between the two lenses is 0.6 meter. We are also given the focal length of the first lens, which is 0.4 meter, again in this case, and F2, which is minus 0.25 meter. All right, so the first step, again, is to find where is the image of the first lens, and this will serve as our object for the second lens. So let's write down the distance formula. So we have 1 divided by the distance of the first object. This is 0.8. Let's write all of these down actually. 1 divided by 0.8 plus 1 divided by the distance of the image. We don't have that value yet. It's the one we're trying to find. And 1 divided by the first focal length, and it's 0.4. If we isolate that value, what we find is that the image is at 0.8 meter. And that brings us to an interesting situation. The distance between these two lenses is 0.6 meter. That means the image go through the second lens in this case. So it go through by 20 centimeters. So there's a distance between the image of 80 centimeter between the first lens and the image. But there's a distance between the two lenses of 0.6 meter. So that means our second object will be to the right of the diverging lens and a distance of 0.2 meter. All right, so I'm gonna give you an instant to write this down, and we will restart by drawing what happened here and how can we solve that part of the problem. All right. All right, so from the point of view of the second lens, we simply redraw the second lens, and now we deal with a new problem with distance of the object. DO2 over here is 0.2, and again the distance of the object is always positive. The focal point of the second lens is equal to minus 0.25 meter. This one does not change. So let's find the image in this case, the distance of the second image. And we get a value for the distance of the second image of minus 0.11 meter. So what does that mean? Well, this means that because we're talking about lens here, if it's negative, if the image is negative, it means it's on the same side as the object, which means the image is on that side now. Distance of the image, so the I2, is over here. And it's 11 centimeter or 0.11 meter. Now we are asked what is the magnification, and the magnification here, use the same principle we used in the previous example, is we simply multiply the magnification of each of the individual optical device. So in this case, magnification is equal to M1 multiplied by M2. It's equal to DI1 multiplied by DI2 divided by DO1 multiplied by DO2. And we get, in this case, minus 0.55. So minus, which means the final image will be inverted, and 0.55, which means the final image will be smaller than the original object. All right, so that's it for question 97.